some of the basic concepts related to power factor improvement and why there is a problem of low power factor in the power system, what can be done, how to improve upon it, and then some simple analytical calculations and examples to understand that how much of what type of power factor improvement would be needed and what would be the capacity of the power factor improvement equipment for improving the power factor from a given level to the desired level. So we'll start with this discussion. So let's start with some of the fundamental concepts. I think by now everyone must be aware of these concepts because we have discussed all this before in this course also. So as we understand, power factor is nothing but the cosine of the angle between the voltage and current in an AC circuit. So this small phasor diagram here represents the idea. So you have the voltage phasor here and the current phasor is at a particular angle phi behind the voltage phasor. So whenever you have this type of, even if they are in line, then also we can define a cosine of this angle phi. So if voltage and current are in the same phase along the same direction,
Sir,
then yeah.
actually I'm not seeing anything, sir.
What about others?
It is visible,
Sir,
Prashant.
visible. Sir.
Okay, so Harsh, I think there is some problem at your end.
Let me check, sir.
So if both these voltage and current, they are in the same line along the same direction, then phi is 0 and cos phi is 1, and that is what we call as the unity power factor. And for all other cases, whenever there is a non-zero value of phi, the phase difference between voltage and current, then this cosine of this phi will be some value between 0 to 1. The worst case will be when voltage and current are perpendicular.
Yes, sir. Now it's visible, sir.
Okay. So when the voltage and current is perpendicular to each other, either current is leading or current is lagging by 90 degree. In that case, cos phi becomes 0. So that is the worst case. The power factor worst case will be power factor equal to 0, cos phi equal to 0. And best case is that when both are along the same line and cos phi equal to 1. And the way we define it by as known as lagging or leading, depending upon whether the current is lagging or leading the voltage. So you have this voltage phasor here, and the direction of rotation of these phasors conventionally is taken as anti-clockwise. So therefore, if your current phasor is above this voltage phasor, that means it is leading the voltage phasor. And in that case, we call the cosine of that particular angle, usually the sign given is negative because lagging is considered as positive. So that case, we call it as the leading power factor, and lagging power factor is when your current is lagging behind the voltage. So also many times we express this as a percentage. So whatever is the value of cos phi, if you multiply it with 100, then you can talk about power factor as a percentage. That is also very common. People talk about 80%, 90% power factor. And if you, in the same phasor diagram above, if you multiply these current values by the voltages, then what you get is the equivalent power values. So you can make a power triangle also like this. And so accordingly, your VI cos phi is along the horizontal line, VI is along this parallel to the current phasor, and then VI sin phi will
Hello,
be
sir.
the perpendicular one. Yeah, who is that?
Sir, your voice is breaking. It's not clear.
What about others?
Sir, little noise is also there, sir.
No,
That's
sir,
why
clear,
I was, sir. That's why I
clear.
was saying.
So some people are saying that it is clear. I guess, I mean, there is no issue from here. I guess the room is not noisy at all. It is very silent.
No,
And
sir,
the noise,
no noise.
right. So I think please look at your connection, don't interrupt the class like this for these issues. So we have this VI is the apparent power, and you have VI cos phi and VI sin phi. So in this case, basically we understand that only when the current is in phase with the voltage, that particular component of power is what is the real power, or which can deliver you the working power, and that is why this is known as the real power or the active power. So that's why if you have Vi along this direction, then the cosine of this Vi cos phi is what is the active power or the working power. And the perpendicular one, Vi sin phi, is the reactive power, also known as the magnetizing power, because this is needed for setting up the magnetic field in an electromagnetic circuit. So even if you have a transformer, or if you have a synchronous generator, or any of these electromagnetic machines, this reactive power, the magnetizing component of the current which is drawn for setting up the magnetic field, will be corresponding to this reactive power and the magnetizing power. So overall, now from this Pythagoras theorem, we can write that your apparent power kVA square is equal to the kilowatt square plus kVAr square. So this is very straightforward, and therefore we can define power factor or cos phi. Again, from this triangle, we can define it as the ratio of your active power to the apparent power, or kilowatt by kVA. So these are some fundamental ideas, definition of basically the power factor. And if you look at the reactive power, it is an interesting concept. It is not delivering any useful work output. The useful work output is coming only from the real component or the active power component. But this is consuming the capacity of your circuit, the current carrying capacity is being consumed. So that's why it says here the reactive power is neither consumed in the circuit nor it does any useful work. It merely flows back and forth in the circuit. So there is a particular, you can say, the current carrying capacity which is occupied by that type of reactive power, and that will not deliver any useful work output. So basically that is something not really desirable, but that has to be supplied again if you have loads of that particular type. So some way, either you generate it at the generating station or through some capacitor bank or some other means, it has to be supplied to make the system stable. The voltage stability has to be maintained, but no useful work output is obtained. So that's why we'll look at, in this discussion, we'll see that there is a lot of need for power factor correction at the user end itself. It's not always possible to generate the entire reactive power at the generator end. Rather, at the distribution end or the user's end, also we can have the compensation for this reactive power. Also, this is one fact which I think from electrical background people might be knowing, but for everyone, that a wattmeter does not measure the reactive power. So we know that the wattmeter reading is always in kilowatts, megawatt, or simple watts. So reactive power is not captured there, and these are the two equations we know for power transfer in a single phase circuit and a three-phase circuit. So VL, IL, cos phi. VL is the line voltage, IL is the line current, and cos phi is the power factor. In a three-phase circuit, it is √3 times line voltage, line current, and cos phi. And this is true whether the circuit is connected in star or delta, irrespective of that. Only what will change is that the values of line voltage and current, line voltage and line current in terms of the phase voltage and phase current, those interrelationship will change depending upon whether it is a star or delta connection. But if you substitute them, the appropriate value of line voltage and line current in this equation, you will get the actual power transfer in the three-phase circuit. So √3 VL, IL, cos phi will hold true always. So now if you just do simple transposition, we can see that your line current in a single phase circuit is P by VL cos phi, whereas in a three-phase circuit it is P by √3 VL cos phi. And now if you fix the voltage and the power level, let's say voltage is anyways fixed for a given circuit in whether you are transmission or distribution level, accordingly there will be a particular voltage level. And let's say the power requirement is also fixed. We have decided, okay, this many number of users are there, this is their power requirement, the real power requirement. So P and VL, if you are fixing, so then you can see that your line current is inversely proportional to your cos phi or the power factor. And that you can get an idea basically here from here, that if your power factor is poor, if this is low, then accordingly you'll have to supply a higher line current for supplying the same amount of power. So that is a non-desirable thing, that is always to be avoided. And what are the disadvantages now of low power factor? From this discussion only, we have covered few things, but now to put it in distinct points. So one is that larger kVA rating of the equipment So your all the equipment which is at the generating end and even in the distribution end, the transformers and all. So the alternator, the transformer, the switch gears, all these are rated in the kVA which it can handle. And as we have discussed that your cos phi is kilowatt by kVA. So if you just transpose it here, the kVA rating is nothing but kilowatt rating by cos phi. So if your power factor is poor, then you need higher kVA equipment for handling the same amount of real power. So low power factor implies larger kVA rating needed. So larger and more expensive equipment for supplying the same amount of real power. Second thing, greater conductor size. So as we discussed, IL is inversely proportional to cos phi. So therefore, if you want to distribute the same amount of power at the same voltage level, because the current requirement will be higher for a lower power factor, so the conductor cross section will be more. So larger conductor size would be needed. That is also, the capital cost investment would be higher needed. And moreover, what will happen is that the running expenditure will be also higher because now the copper losses or the ohmic losses in the circuit will be higher. Because as we discussed earlier also, the copper loss or ohmic loss is proportional to I square, it is equal to I square R. So it is, poorer the power factor, higher is the current flowing in the circuit, and the losses, the ohmic losses are proportional to square of that current value. So not only it will require a greater capital expenditure as per point number 1 and 2, but also as per point number 3, it will have a larger running expenditure also. So it's not really a desirable thing. And another thing is regarding the poorer voltage regulation. So as we discussed earlier also that voltage regulation means whatever is your no load voltage when you have a full load loading, then there is a drop in the voltage level. So in this case, as we discussed that if it is coming again from the same relationship, IL proportional to 1 by cos phi. So if you have a low power factor, there is a larger current flowing in the circuit, and if there is a larger current, that will cause a greater voltage drop. So, across the circuit from alternator to transformer to the transmission and distribution lines. So this is also not desirable. You don't want the voltage drop. We have discussed earlier also that there are some limits, plus minus 6% usually at the final user's end for the voltage limits. So this is also an undesirable effect. This low power factor will lead to more voltage drop and decreased voltage available at the user's end. To keep receiving end voltage in acceptable limits, voltage regulators would be needed. So another expenditure in terms of the voltage regulators. And finally, reduced handling capacity of the system. So as we discussed that the reactive component of the current, that will also occupy some of the current carrying capacity of the circuit. So it prevents the full utilization of the installed capacity. So even if you have because the kVA rating is fixed, but out of that something is going to the reactive power. So the more the chunk going to reactive power component, so the actual power which you can deliver, the real power or active power, will be reduced. So the handling capacity of the system is reduced. So these are some basic concepts and some disadvantages of having a poor or a low power factor. Any questions or any discussion so far?
Sir, this is Prashant.
Yes, Prashant.
Sir, it is for distribution line only or for transmission, distribution, any line?
Yeah, so see the effect comes from the distribution side. So basically what happens that distribution side, there are different loads which are having this type of a poor low power factor profile. So ultimately it has a loading. So if distribution side is asking for more and if you are not as we look at this, that one option is that you compensate it at the distributing end on itself. But if you don't do that, then it will have a loading on the sub transmission and then the transmission and then the generator end. So it will have a cascading effect. It is originating from the distribution end itself.
And sometimes, sir, many times we put that means voltage devices in the transmission also.
Correct,
So
correct.
that is due to distribution, that means line effects, you can tell. Load effect.
Yeah, the loading ultimately is coming from there, but you want to, the voltage regulators will be placed, at different places across this entire thing. So, usually the substations will have a voltage regulating device so as to maintain that voltage at the proper level, and in terms of the power factor also capacitor banks and all will be there at these substations.
Okay.
Yeah. And these days there are these FACTS devices, the flexible AC transmission system devices, which will have power electronic based circuits for supplying the reactive power in a variable mode instead of just having a fixed capacitor bank. So all those things are there for helping improve the power factor.
Sir, please explain the last point, sir.
Yes, Anvesh. What's the
Sir,
confusion?
last point, sir. Reduce handling capacity for use.
Yeah, reduced running capacity. Why? Because the circuit has got some current carrying capacity, right? And now what is happening is that you have to accommodate, if the power factor is poor, you have to accommodate for this reactive power also. And this reactive power, ultimately, it's not going to deliver any useful work output. It is just circulating in the circuit. So the idea is that how much of real power you can deliver to the consumer's end, or transfer through your circuit, that will be reduced. Okay, so that is the point there.
Okay, sir.
Anything else? Okay, so let's move ahead. So let's also look at the causes of low power factor, and some of the prominent causes are listed here. So one of the traditionally this used to be the cause, and I mean now there are many more. So the AC motors, they are always inductive loads, and also the power factor also varies for the AC motor, because when the motor is starting, then there is a high component of the magnetizing current, and the starting current is very much having a poor power factor. So when the motor is starting, or it is having a light load, then the power factor is really poor. It is in the range of 0.2 to 0.3. But then as it builds up, then what will happen, that the load component of the current which it draws becomes more significant as compared to the magnetizing component. So ultimately at full load, it operates somewhere in that range, 0.8 to 0.9 power factor. But especially during the starting phase, it is having a very poor power factor. And also during operation, the power factor is not unity, because it's an inductive load. So that is one traditional source of low power factor. Then there are several other devices and equipments, like you have arc lamps, electric discharge lamps, CFLs and tube lights are very common these days, industrial heating furnaces and welding machines. All these are typical examples of which contribute to poor power factor. Power electronic equipment, as we discussed in earlier class also, it's a major source. And so all the IT load, the information technology load, which we the computers and laptops and all of those circuits having power electronic chips and this type of equipment, that will always cause the poor power factor. And during low load period, supply voltage so this is not really prominent effect, but yeah, also you can say secondary effect is that when you are having a low load period, so what will happen, that the supply voltage is increased relatively, because the load is lower. So during that time, due to this increased supply voltage, the magnetization current in all the devices which are there in this, the transformers or other devices which are there in the circuit, they will draw slightly higher magnetizing current, and which will have a further effect of lowering the power factor. So all these effects, so basically, as you can see, it is emanating from the user's end, and as the variety of electrical gadgets and especially the electronic items is increasing, this problem is becoming sort of more prominent, and it has got an effect on the entire system operation. So let's look at how we can improve power factor. We'll look at some conventional methods. There are some advanced methods also, as I said, about the FACTS devices and all. So right now we'll just keep our discussion to the simple methods. Conceptually we'll discuss, and devices can be many more also. So usually what we see, that despite this large variety of loads which are there in the power system, and some of them are inductive in nature, some are capacitive in nature, and there's a lot of variety. But still, overall, if we see at the present what is the nature of the load in the current situation of the power system, we see that overall the load is lagging only. It's an inductive load overall, if you consider. So in the bulk power system, or at any particular system, if you take any practical real life system, you'll see that the aggregate effect of all the different types of loads is that the overall power factor is lagging. That's drawing a lagging current ultimately, or you can say it's an inductive nature load. So in that case, what we want to do is that to improve the power factor, if we can connect some device which takes leading power in parallel with the load, if you can connect, then that particular thing can help improve the power factor. And this device, the simplest of this device is the capacitor. So this figure will help you understand it further. So if you see, this is inductive load. You have R, the resistance, and L, the inductance. So there is a RL load, inductive load, and there's some voltage from where it is being supplied, and it is drawing some current I. So let's say the phasor relationship is like this. You have the voltage as the reference phasor, and current is lagging at this angle phi1. Now what we did is that in the second case, we put a capacitor in parallel to our original load. So now what will happen is that this capacitor will also draw some current, which is indicated here as IC. And as we know that capacitor is having this relationship that whatever is the voltage source to which it is connected, the current which the capacitor will draw will lead the voltage source by 90 degrees. So this IC, if you want to put it in the phasor diagram, this IC will be leading the voltage by 90 degrees. And now if you see, so basically, as we know, everything in electrical circuits, it's all phasor addition or vector. You can understand analogously as vector. I mean, the concept is similar. So now the current which this will draw from the source, we are calling that as I dash. This I dash will be IC plus I, right? So both these loads now, the original inductive load and the new capacitive load which you have introduced in the system, both of them have to be supplied from the source. So now the new current I dash is IC plus I. And if you do a simple vector addition or phasor addition here, you can see that you have your phasor I here and phasor IC here. So the phasor summation of the two will give you this I dash, which is in this case, it is coming out to be slightly leading. You know, this phi2 is the phase angle of I dash with respect to V. So this I dash is leading V by this angle phi2. Okay. So this is the principle behind power factor improvement. And now, so basically, because the nature of the loads is inductive, overall it is inductive. So basically what we need to do is that we need to have some sort of a capacitive device. Now this capacitive device can be of different types. One option is that you just have a simple capacitor bank, a group of capacitors which can supply a particular reactive power to the system. Another option is that you can have synchronous condenser, what is known as, we'll look at that, the synchronous machine operating in the overexcited mode. Or then there are other options. There is something known as the phase advancer, and these days there are these power electronic devices like STATCOMs, static compensator, or SVRs, and different other new power devices, which are power electronic devices, which are known as the FACTS devices, FACTS, flexible AC transmission system devices. So the idea with them is that the new and advanced power electronic FACTS devices, the advantage with them is that they have a flexibility, I mean, in terms of how much reactive power you can put, and also you can, if needed, you can change the nature of the reactive power. So instead it can supply capacitive power, but also you can change the settings to supply the inductive load from the same device. That is also possible. So greater flexibility is possible. But the basic principle remains same, that you have to, whatever is the nature of the load, if it is lagging in nature, then you need to supply a leading load to cancel it out. Suppose if the original loads are capacitive in nature, then you need to supply a inductive load. So if this I, the initial load current, would have been leading, then we would have added a inductor and we would have cancelled it out by supplying a lagging load. So that is the basic fundamental principle. And also in this figure, as you can see, that when you added this capacitor IC, which is drawing current IC, now the new current I dash is actually less than I in magnitude as well. So the current capacity needed is also reduced. and the active component of the two is same. So if you take the projection of this vector I on the horizontal line and the projection of vector I dash on the horizontal line, both will be same. So your I cos phi 1 is equal to I dash cos phi 2. And if you take their projections on the vertical axis, y axis, then what you will see is that this I dash sine phi 2 is nothing but the difference of these two. In this case, it will be IC minus I sine phi 1 because IC is more. IC here turns out to be more than your I, the vertical, the Y component of your original current I. So because IC is more, that's why the overall current is still remains capacitive in nature. So here what we can write is I dash sine phi 2, the Y component of I dash is nothing but IC minus I sine phi 1. That we can write it out here. And if you see here Vi dash, so if you just multiply this equation with your voltage value, so Vi dash sine phi 2 equal to Vi sine phi 1 minus Vic. So you can say that the net kVAR after power factor correction. So what is the net reactive power demand after you have done the power factor correction is nothing but your lagging kVAR before power factor correction minus the leading kVAR of the equipment. So there was some kVAR, that is the unit for reactive power. So there was some kVAR requirement, some reactive power demand in the system. And now you have nullified it by introducing the reactive power demand of the opposite nature. So you have the lagging kVAR before power factor correction minus how much is the leading kVAR which you have introduced. The difference of the two will give you the net kVAR after this power factor correction. So, and you can look at this equation and also see that if your leading kVAR of the power factor correction equipment is lesser, then what you will get will be still the resultant net kVAR will still be lagging in nature. But like in this example here, the leading kVAR of the equipment is more than the lagging kVAR originally there in the circuit. So you get the net kVAR as negative, or which means negative sign indicates that it is capacitive in nature. And that's why I dash is leading V. So that is the fundamental principle. Okay. Any questions so far? Then we'll go to the equipments.
Sir, in this note, first point, this I dash should be greater than I, sir, because I dash is a summation of IC and I. So.
So will it be greater? What do you say?
Yes, sir. I dash should be greater than I.
Can anyone answer that question?
No, sir. It will be less. From
Nitish, can you explain?
Sir, vector triangle will give the answer. Like if we shift this IC to this head of I, then we'll see that the resultant will be smaller than I.
Right. Someone else is saying something?
Yes, sir.
Yeah, who is that? Rajat?
Yes, sir.
Yes, go ahead.
Sir, actually, sir, I dash is the phasor sum of the IC and inductive and capacitive load. So, sir, I dash will be less than the complete I.
Right. Right. So, whose question was this? Pranit? Or
Sir,
Pramod?
Pramod.
Pramod.
Yes, sir.
So Pramod, did you get what these two people told? I mean, Nitish and Rajat, what they said, is it clear?
Sir, means it's a phasor sum, no, sir.
You have to understand that thing, that it is not just simple number sum.
Okay.
If it is simple scalar numbers, then always this I dash will be greater. But here there is a sign which is involved. Okay, and due to that particular thing, because as you can see from the phasor diagram also, so as Nitish said, you can look at it in terms of the phasor diagram also, or as the other person Rajat also said, that basically what is happening is that one is lagging, another is leading. So they'll have a cancellation in terms of their components. And so that's why due to that phasor summation, your magnitude of I dash is actually lesser than your I. Okay. And you can visibly also, you can see, if you look at this phasor diagram, you can see, that the active component of the two is same, I dash and I, the active component is same, but the reactive component of I dash is much lesser than I. So obviously I dash has to be less than I. Okay.
Okay, sir.
Other questions?
Clear, sir.
Yes. Go ahead. Who is that? Anvish?
Yes, sir. I said clear, sir. We can go ahead.
Acha, I thought you said yes. Okay. So this was the basic idea and basic concept behind the power factor correction. Now let's look at some conventional equipment which is used for power factor improvement. So typically what we see is that if you have the generating station, like we discussed the generating station in detail in previous classes, the generating equipment is there, there is this excitation control and governor and all those things are there. So basically the excitation control is what will be the important thing with respect to power factor as well. Because if you recall, there was this phasor diagram which we drew earlier, the V phi, and there was EA and there was the current. And if you change the magnetic flux in the machine, then the EA changes and accordingly your current and voltage, they also adjust, and the not just the magnitude of the voltage but also the power factor also changes. So in this case, the thing of interest for adjusting the power factor would be the excitation system and the excitation control. So overall, usually what we see is that for a typical large generating station, we experience that the power factor, overall power factor of operation for that large generating station might be in this range 0.8 to 0.9, which is still acceptable. But suppose if it is going lower, if it is going less than 0.8, then it definitely becomes a cause of concern. And then we need some other equipment to improve this. And as Prashant was also saying some time back, is that this equipment for power factor improvement can be placed at different places in the overall power system. So you can have these power factor correction equipment at the generating station itself. You can have it in the transmission system also. You can have it at the distributing end also. And usually it's a mix of it. At different places we have these capacitor banks or other power factor correction equipment. And we need to ensure that overall the system is operating at a reasonably good power factor. So some of these examples are given here. These three, typical the conventional devices. One is the static capacitors, another is synchronous condensers, and third is the phase advancers. So we'll look at these one by one. So static capacitor is just your simple capacitor with appropriate rating, obviously. So appropriate voltage and current rating should be there. How much power it can handle and what will be the rated voltage at which it will operate. But it is a simple capacitor, as we know. So it's a usual capacitor connected in parallel with the equipment. So if you have a three-phase load, then you can connect these three capacitors, set of capacitor banks, either in delta or in star connection. Either way, the voltage and current relationships will change accordingly. The voltage and current rating of these capacitors will be decided, but ultimately the reactive power which they will pump into the thing will be same. So capacitor draws a leading current and partly or completely neutralizes the lagging reactive component of the load current. So we have discussed this already, that it draws a leading current and there was a lagging current which was initially there. Now you are drawing a leading current. So either partly or completely it will neutralize the effect of the lagging reactive component of the load which was there. Some advantages of this, it is a very common thing. Capacitor banks have been used for several years now in the power systems. So some of the advantages are that it has low losses usually and requires little maintenance as there are no rotating parts. These are all static capacitors we are talking about. It can be easily installed as they are light and require no foundation. So any substation or any particular place we can easily install them, and can work under ordinary atmospheric conditions. There are no special conditions needed for its presence. So these are some advantages. Disadvantage is that it has got short service life, usually 8 to 10 years. I mean, one might say that is also significant, but when we are talking about the power system, the lifespan is of several decades. So This is relatively a shorter lifespan. Easily damaged if the voltage exceeds the rated value. So that is one thing that they are delicate in that sense that if the voltage exceeds a particular, obviously there will be some safety margin above the rated value, but if it goes above that, then it gets damaged. And once the capacitors are damaged, their repair is uneconomical. So basically, if it is getting damaged, the only viable economical option is that you replace it. So those are a few of the disadvantages. Then second is the synchronous condensers. And the synchronous condenser, as I said, is that it is basically a synchronous motor which is operating at no load and in overexcited condition. Overexcited means that whatever is the, there is a rated value of field current which will generate the rated value of flux in the machine. And if you exceed that rated value of field current by a suitable margin, not exceeding the thermal limit of the machine, but having slightly higher, let's say, rated field current, then the flux in the machine is higher, the EA which it will generate would be higher, and you can see when you analyze it with the phasor diagram, what you'll get is that the overall current which it draws is a leading current. So this three-phase synchronous motor in the overexcited mode, it works same way as a capacitor. As if you attach a capacitor bank, it will draw the leading currents from the source. Same way, this also does the same function. So if we attach this three-phase synchronous motor and operate it in the overexcited zone, so what happens is that it draws the leading currents, which are shown here as IM. And IL was the original load current which your three-phase load was drawing. So again, the same thing, but only difference from the previous, when we looked at the capacitor phasor diagram, we said that IC or the capacitor current is exactly 90 degree, leading by 90 degree with respect to voltage. But this will not be exact 90 degree. This will be a high value, but and how high it will be will depend upon how much it is in the overexcited zone. So, but accordingly, it will definitely be having some leading value. So here is, if you notice, this IM is leading your voltage V, but not by 90 degree, by some value for some angle less than 90 degree, and that angle is indicated as phi m. So this particular thing will be depending upon the characteristic of that particular synchronous machine, what is its phasor relationship, and what is the rated value of field current, and how much overexcited we are running it. So depending upon that, there will be some leading current. And again, the same concept, conceptually it is same, but now it will be the net current here, I, which will be drawn from the source, will be again the phasor summation of your IM, the motor current, and the IL, which is the load current. So IL was lagging earlier by this angle phi L, and IM is leading by phi M. And if you just do simple vector addition for these two, you can see that the net current is I, and it is very significantly improved. So the power factor has improved from phi L to phi. So that is the idea here. And one note is given here is that maximum leading power is taken by a synchronous motor with maximum excitation and zero load. So that is the idea. We are operating this at no load because we don't want to draw any, work output from this synchronous motor. We are just using it as a capacitor. That's why the name synchronous condenser. Condenser is another name for capacitor. So the idea is that we want to have operated at maximum excitation. So whatever is the maximum excitation possible, considering the thermal limit of the machine, because if you recall earlier that the limiting value is always the thermal limit, either for field circuit or for the armature circuit. So with respect to that thermal limit, whatever maximum excitation is possible, if we can run the synchronous motor with that maximum excitation and zero load, then it will draw the maximum leading power, and accordingly maximum improvement in power factor will be resulting from that. And this option is not very common because of several reasons. We'll look at the advantages and disadvantages, but so it is usually used only at major bulk supply substations, and not at smaller substations, and many times at the generating end also. So let's look at first the advantages. So advantages here: by varying the field excitation, current drawn by the motor can be changed by any amount. helps in achieving stepless control of power factor. So that's interesting. I mean, before the power electronic devices came, the STATCOMs and SVRs and all came, because they ensure, the power electronic devices ensure a smooth control of the power factor. But before that, typically what people were using was these capacitor banks. So as you can understand with this capacitor bank, something similar to the discrete resistance as we studied for the ELC, discrete resistance type ELC. Something similar is that you will always have some discrete number of capacitor banks. So maybe, whatever is the rating. So if you put one capacitor of a particular rating, X rating in each phase, then maybe you can make it 2x or 1.5x and 3x or 5x or 10x or whatever, but it goes in discrete steps. The intermediate values might not be possible. But with this, that intermediate or the smooth value variation of the power factor is possible, because here we can vary the field current, which is a continuous current. We can always vary it in a continuous fashion, and accordingly the amount of excitation will change, and accordingly what will be the net power factor can be varied in a stepless manner, in a continuous manner. So that is one advantage over the capacitor banks. Then another thing is that motor windings have high thermal stability to short circuit currents. So stability is better. Like here, as we said, that if the voltage exceeds the rated value, it gets easily damaged. This is more robust in that sense, because we discussed about the thermal stability. We have already discussed about the winding thermal stability. So for some time it can take some particular short circuit current also. So it will not really burn out that easily. So with respect to, remember references with respect to the capacitor bank. And faults can be removed easily. So those are some of the advantages of this. And disadvantages, if you look at it, so there are still considerable losses in the motor, whereas that was the advantage with the capacitor bank, was that there were low losses in this, but here there will be losses, both mechanical or electrical losses. And electrical losses will be less because we are operating at zero load, but still there will be some loss, stray losses and all, but mechanical losses will be there. So there are some losses in the motor. The maintenance cost is high. That is one prominent disadvantage, because this, as we can understand, this will be a large machine typically. These are used for large installations only. So a large machine and having rotating parts, so maintenance will obviously be high. Produces noise as it operates. That is a secondary point. And in the economics of it, that is interesting, is that, as it says here, except in sizes above 500 kVA, the cost is greater than that of static capacitors of the same rating. So if you just compare the economics of the two, the capacitor bank and the synchronous condenser, then for any value, any size below 500 kVA, capacitor banks usually are typically more economical. But for larger sizes, for size above 500 kVA typically, you find that this is more economical. So that's why it says here, except in sizes above this, that means below this particular limit, the cost of synchronous condensers is higher. So they will be used only for large. That's why it says here the major bulk supply substations. So if you are having a large generating station or some large transmission substation, only those places this might be economical, in sizes above 500 kVA. Otherwise, it's not economical. And synchronous motor has no self-starting torque. Hence, auxiliary equipment has to be provided for this purpose. So that is also another characteristic of the synchronous motor. Unlike the induction motor, this is not self-starting. So you need to have some auxiliary motor or something to initially, start the rotation of the synchronous motor. So that is also another extra expenditure. So those are the advantages, disadvantages of the synchronous condenser. And now let's look at the third type of equipment, which is known as the phase advancer. And this is typically used, it has got traditionally it has been used for improving the power factor of the induction motors. Because if you look at the list of loads which we said here, which are causing this poor power factor, out of these, traditional equipment was this AC motor loads. Those were traditionally present since several decades, right from, the time we are using generators, since then only motors are also there. So motors have been traditionally the source of poor power factor. The other equipments, as we can see, they have come up later. So that's why this phase advancer is specifically dedicated to improving the power factor of the induction motor. So in the induction motor, what happens? What is the reason? As it says here, the low power factor of the induction motor is due to stator winding drawing the exciting current, which lags behind supply voltage by 90 degree. So the magnetizing current for setting up the magnetic field in the machine, that is almost purely inductive or close to pure inductive. So that's why the it is very severely having a very poor power factor. Phase difference is almost close to 90 degree. So the idea is that if we can somehow compensate this exciting current through some other source rather than drawing from the supply, then the very poor power factor which the induction motor exhibits in the starting phase, that can be compensated. So that's what it says here. If the exciting ampere turns can be provided from some other AC source, then this particular effect can be nullified. So this phase advancer is nothing but an AC exciter. Okay, so it is similar to please understand the reason is different. The name is similar. Like we have been talking about the brushless exciter for the synchronous generator. There it was a different reason, because the reason was that it was not really convenient to supply your DC supply to the rotating part, and so that's why we had that exciter. That was one of the primary reasons. Here the reason is different. Here the reason is that your induction motor is still drawing. It needs some magnetizing current to set up the magnetic field. So if you don't provide anything separate, it will draw that magnetizing current from the supply, and the power factor will be poor. So the idea is that we want to have another AC exciter which can supply that magnetizing current. So this thing, it is mounted on the same shaft as the main motor and is connected to the rotor circuit of the motor. It provides exciting ampere turns to the rotor circuit at slip frequency. By providing more ampere turns than required, the induction motor can be made to operate on leading power factor like an overexcited synchronous motor as well. So it is similar to your small AC generator, and the idea is that it is providing that extra amperage which is needed in the starting phase, basically for the setting up the magnetic field in the machine. So it is mounted on the same, as it says, it mounted on the same shaft as the main motor. So some advantages of this is that phase advancers can be conveniently used where the use of synchronous motor is unadmissible. And disadvantage is that it is not economical for motors below 200 horsepower. So again, this is also all these, like synchronous condenser was also for a large sized substation only. Same way, your phase advancer is economical only for large sized induction motors, because you are installing a separate AC generator sort of thing, so on the same motor shaft. So it will not be very economical for small motors, but for motors above 200 HP, this will be economical. So this is specifically dedicated to the induction motors. Then calculations and all we'll take up in the next class. Any questions anyone is having? Let me know.
Sir, in synchronous condenser, always the resultant current will be lagging, sir.
No, not necessary, Anvesh. It's always a phasor summation. So it will depend upon the relative value of IL and IM, and also the relative the phase angle. So it will be just you will just have to do the vector summation each time, and it will depend on what is the phase angle phi m, what is the phase angle phi l, what is the magnitude IM and IL, and you'll do the phasor summation and you can get the actual phase angle. So if IL is relatively having a better power factor, that means this phi L would have been lesser, then it's quite possible that I would have gone leading. So it's just the relative values of phi M and phi L which will determine what will be the final outcome, whether it will be leading or lagging.
Okay, sir.
But one thing is for sure, that this phi M will be less than 90 for sure. Phi M cannot be 90 here, because this will draw magnetizing component, but also some real component also synchronous motor will draw even at no load. Though it is at no load, but some of the real component will always be there. So this phi M will be less than 90 degree, that is for sure.
Okay, sir.
And anything else? Okay, so we will stop here and continue on next class in Thursday.